So today we're going to talk about atomic orbitals and what that term actually means, and basically how to get more in depth and more accurate about the structure of this space in an atom around the nucleus, where electrons are found. So just a quick refresh, we've discussed how Niels Bohr came up with the Bohr model in 1913 of the hydrogen atom, where in a nucleus, in an atom, we have the nucleus in the center, and around the nucleus are these rings where electrons, we'll use an orange dot here to represent an electron, where they orbit around the ring, around the nucleus in these specific determined paths. So this is kind of like planets around the sun with fixed paths. Okay? This atom has 3 electrons in it, so therefore it would be an atom of lithium. Okay. It has 2 energy levels, n equals 1 and n equals 2, according to the Bohr model. But then about a decade later, in 1926, a mathematician by the name of Schrödinger, S-C-H-R-O with an umlaut, Schrödinger, came up with a different model that described the structure of electrons and the space around the atom using mathematically, using some advanced math that we don't actually need to get into at this point. You probably will in the more advanced chemistry courses. But what he defined an orbital as is orbitals were not these specific pathways anymore. He said that's not actually true. That's not actually representative of electrons and where they orbit around the nucleus. What orbits actually are regions or areas of space in atoms where there's a 90% probability, a chance, of finding an electron. And again, there's a famous equation called the Schrödinger equation that can be solved with some very advanced mathematics to prove what these regions look like. But this is a pretty radical idea. We're getting away from this idea of fixed orbits and actually saying, well, no, electrons aren't in fixed orbits. We do have data, emission spectra, I should say, that show there's only certain bands for different elements, which means that there are only certain energy levels where electrons can be found. But those energy levels don't really look like rings anymore. They're actually 3-dimensional areas of space. So what do I mean by that? Well, when you solve the Schrödinger equation for 1 electron in an atom of hydrogen, okay, what you find is there's an unlimited number of places for where the electron could be. But some locations are much more likely than others. There are some places in the atom where an electron is much more likely to be than other places. So what we see here is we have a plot of xy plane and the z-axis, so 2-dimensional. Remember, we're taking a 3-dimensional object, an atom, and making it 2-dimensional. So in the center of that atom would be the nucleus. So let's think back what we know about the nucleus. The nucleus is positively charged because it has protons in it. So we have positive charged nucleus. Let's say this is an atom of hydrogen. And then we have electrons floating around somewhere around this atom. Well, where are they going to most likely be? Well, let's just think about laws of attraction. Since this is negatively charged and this is positively charged, they're oppositely charged. These are going to want to be close to each other. So since the proton can't move in the nucleus, really, this electron is going to want to be as close to the nucleus as possible, if it can be. So, it might be right here, but it could also be here or here. There's all these different locations, but it's most likely going to be as close to that nucleus as possible, because that's its most stable location. if we think about all the possible places that the electron could be around the nucleus, some are much more likely than others, and that's what we're seeing in this plot here. Where the color is a lot thicker and a lot darker orange, we can kind of see here near the nucleus. That is what we define as an orbital. Of all these unlimited dots, what's the space where 90% of them fall? Because remember, Schrodinger said that's where 90% probability is of finding an electron. So that's about in this space here. And remember, this is three-dimensional, so you have to kind of try to imagine this as a three-dimensional object, like a sphere, like a globe. Okay? So this is the space where we're really likely to find an electron. It could exist out here, but it's much less likely. Okay? The closer we get, as a little bit of a review, remember, closer to nucleus equals lower energy. And the reason for that now is clear, because the closer we get, the more stable this interaction is, because those opposite charges are closer to each other. The further you pull this electron away, the more unstable it becomes, because it's further away from that positive charge it wants to be next to. These equations can be solved to determine all these different orbital shapes. There's still different energy levels like we've talked about before, N1, N2, N3, and etc. But what we're seeing now is within each energy level, there are different shapes, different regions where those electrons could be. So the lowest energy level is called the s orbital. So this is the lowest energy level. Okay? The lowest energy orbital, I should say. Okay? The s orbital is very simple. The s orbital just looks like a sphere. And that's easy to remember because it begins with an s. The s actually doesn't stand for sphere, but it's an easy way to remember that, boom, here's our region. Inside here, there's a 90% probability of finding an electron. So s orbitals are the lowest energy orbitals. What you need to be able to walk away with from that is, if I gave you pictures of orbitals, you would know that the spherical one is an s orbital and that it's the lowest energy one. What is next? If you go to the next higher energy orbital, those are called p orbitals. Okay? So these are the next most energy after s orbitals. And again, the p doesn't stand for anything in particular, but if we took electrons and we plotted where we would find the highest probability of finding those electrons, we would get some things that look like this. There's a probability of finding them kind of up here, but also down here. And since these are three-dimensional objects, atoms are three-dimensional, there's three axes where these shapes could be. So those orbitals are named based on their axis. So here we can have the pz orbital, here's the px orbital, and here's the py orbital. If you're curious, the P stands for principal, and that comes from when scientists were first looking at emission spectra. That's what they named the bands that were emitted by these orbitals. But you don't need to worry about this, just a side note. So what do you need to know about the p orbitals? There are three p orbitals. You need to know that those are the px, the py, and the pz, and that they have this shape, kind of like a dumbbell, which is it's sometimes referred to as a dumbbell here. Here, this one you can see is on the z-axis. Here, this one is along the x-axis. And here, this one is along the y-axis. Again, these are predicted and solved for mathematically. We don't need to know the math. All we need to know is that the p orbitals have more energy than the s orbitals. There's three of them, and that they are called the pz, px, and py. And they have these particular shapes. What about the next energy orbital? The next orbitals are called the d orbitals. And again, side note, d orbitals stand for diffuse. And again, that was what the emission spectra lines were called, which were emitted when electrons moved out of these orbitals. What you need to know about the d orbitals is that there are 5 of them, and that they are more energetic or higher in energy than the p orbitals, and that are higher in energy than the s orbitals. So it's kind of like s, P, and then D. What are those 5 shapes? Well, these ones are pretty straightforward. You can kind of tell it's kind of like a dumbbell here, and then a dumbbell here, and then another one going up in the other direction on this axis, and down here. I'm going to build models of these out of balloons in class, but if we kind of turn this on its side, it would look like something like this. Boom. Or something that looks like this. Boom. Okay. Again, these are regions of probability. They're solved mathematically. This one looks pretty cool. Okay, it's got this dumbbell shape, but then it also has this ring around it. Okay. One thing that's just another note, if we go back to the p orbitals, you notice at the center here, there's no electron density. It's impossible to find an electron in the p orbital that's right near the nucleus. That can only be for the s orbital. The last thing we need to walk away with is we've talked about how energy levels still exist. N1, N2, N3. The idea is that within each energy level, these orbitals exist. Within the first energy level, there are s orbitals. Within the second energy level, there's s orbitals and d orbitals. And within the third energy level, there's above I should have said p. And in the third energy level, there's s, p, and d orbitals. There's another set of orbitals after that called the f orbitals. We're not going to get into them now, but we're going to break down what you need to walk away with today. The understanding that Schrödinger determined that orbitals were regions in space where there's a 90% probability of finding an electron. And he proved that mathematically. The reason why electrons would want to be closer to the nucleus is because there's this electrostatic attraction between opposite charges. So the most stable, the lowest amount of energy possible, is closer to the nucleus. The lowest energy orbital is called an s orbital. There's only one of them. It's a sphere. After that comes the p orbitals. There's 3 of them, which have this shape along the different axes. And then the d orbitals. And there are 5 of them, which have these different shapes.